declared in where we have both the superclass and the subclass in the object declaration. If we called that shared method on like this new object that we created, which method do we use? So basically, the way to answer this is, oh, sorry. Okay. Okay, so the way to answer this. So a couple things that you need to know. The first thing is that whenever we declare an object, that we declare has a static type and a dynamic type.
Are you speaking into here?
Yes.
Their audio. Let's see. Can it's so bizarre. You know which audio system we're supposed to use? Can you hear us better through this? No. Where the microphone's supposed to be? Oh, I see. Okay, so it sounds like you'll have to just stick close to this. Yeah, stick close to the computer, sorry.
Okay.
Yeah. If you want people in the room, you can also people.
Okay, so good. Can everyone hear me okay? Okay, perfect.
Yeah. Let us know if there are any more audio issues.
Thanks. Okay, so like I said, whenever we declare an object, that object has a static type and a dynamic type. So the static type is going to be whatever is left of the assignment statement. So in this case, that's going to be dog. Another thing just to keep in mind is that static type is declared by like our program during compile time. Dynamic type is declared at runtime. Not like the most important, but I think important to keep in mind. And then every object has a dynamic type, and that's going to be whatever is right of the assignment statement. So the thing about static type is if your static type and dynamic type are different, you may be wondering, like the object that we're declaring, in this case, it's called S. Which class does it belong to? S is going to be an instance of the dog class. That is something important to keep in mind, that whatever the static type is, the object is going to be an instance of that. One quick exception is casting. So if the object is, this should say, and like that second bullet over there, that should say Shiba instead of dog, my mistake. But if an object is cast to be something different than its static type, in that case, then the class that the object belongs to changes. Otherwise, the class the object belongs to is going to be whatever is its static type. Does that make sense to everyone so far? Okay, cool. So here's the rule with DMS. If you have a superclass and a subclass, or if your static and dynamic type are different, and they, in both classes, like the superclass and the subclass for which you're declaring the object, if they share a method, so I guess like a good example of this would be here. Here, like you can see that we have the greet method in both the dog class and the Shiba class. Which one do we use, the one in dog or in Shiba? The rule is that if the shared method is overridden in the subclass, and if it's not static in the superclass, you use the implementation from the subclass. Otherwise, you use the implementation from the superclass. That's like the singular, if you remember one thing from like this section, that is the most important thing to remember. However, one other thing to remember is that like you may be wondering what's the benefit of using two different classes while declaring this object. So the object actually has access, even though like we've said before, our object X here, even though it belongs to the superclass, it still has access to the methods in the subclass. So if like, let's say we have a shared method that is not in the superclass, if it exists in the subclass, and you call x.shared method, then you use the implementation in the subclass. But keep in mind that the rules before still apply. Okay. Anyone have any questions about that so far? Okay, wait, use the mouse, use the pointer. Okay. If it's static in the superclass, you're going to use the implementation in the superclass. Yeah. Okay. One final thing, I think this is my last thing. So when you're making declarations where the static type and the dynamic type are different, you're allowed to have a declaration where the static type is a superclass of the dynamic type. However, the other way around is not allowed. And the way that I like to think about this is that, so whenever you make a subclass like extend a superclass, you're adding more information to whatever object you're creating, if that makes sense. So like in the case of like the dog and Shiba example, if you create an object that, if you create a Shiba object, then it has all the information from the dog class plus stuff in the Shiba class. So you're allowed to like add information into whatever object you create, but you cannot take information away. So like in the case of like the dog and Shiba example, let's say like you have a static type, you have a static type being like the Shiba, you have a static type belonging to the Shiba class, and then the dynamic type belonging to the dog class. Basically, what you're telling your compiler is that like the object's dynamic type is going to have less information than that of the static type. That is something that is not allowed in Java syntax. Yeah, I think that's basically it in terms of content. I had a couple practice problems that I'm going to give you guys like a couple minutes to go over this, and then I'm going to go over that, and then there's one more. So I'll give you guys like 1-2 minutes to go over that. Okay. Does anyone have an idea to what would be printed out when we run this? It's okay if not. No. Okay, no problem. Let's go over the answer. Okay, so the explanation for that is right here, but basically, so we saw in our question that D is going to be an instance of the dog class, right? So when we look for when we run the method d.getType, hold on. Okay. So when we run this method, basically, so we see that the getType method is static, and because of that, even though the getType method exists within Shiba, we're still going to call the method from the dog class because we do not override it in the subclass again because this method is static. Does that make sense to everybody? Am I running out of time? No. Okay. Okay, perfect. Okay, this is the second practice question. It's a little bit longer, so I'll give you guys like 3-4 minutes to go over that, if we have enough time. Okay, cool. Okay. Does anyone need some more time going over that? Okay, cool. So for the first question, does anyone have an idea about what would be printed? Okay, my next slide basically I think has all the answers, so let's go to that. Okay, so it's actually going to be a compile error. And the reason for that, because, okay, so the dog, so, okay, first when we declare Dan over there in our declaration, there aren't any issues because we see that the static type is the superclass, the subclass, the dynamic type is the subclass. Everything is all good there. So we're calling the play method on Dan. So the first thing that we do is that we look into the dog class to see if there is a play method. We see that there is no play method. Because of that, I believe it is a compile error. I just wanted to double check on that, if that's the right reasoning. I don't think that's right, actually. It's because the dog class doesn't have a play method? Okay, wait, so then the dynamic type doesn't have access to everything. Okay, okay. Yeah, I'm so sorry. What I said before was actually not right. So I said before that like whatever you declare, in this case, like the Dan object would also have access to the methods in the Poodle class. I think that is actually wrong. That is not true. And that's why in this case, we're getting a compile error because the dog object does not have access to any play methods. There's none of that in the superclass. My bad on that.
I'll interject a little. Technically what's going on is the compiler, when the compiler initially compiles the program, it doesn't have access to the dynamic types of objects. So the compiler doesn't even know that the Dan object, the Dan variable, is being assigned to Poodle, which is the dynamic type for Dan. So because the compiler doesn't see that, the compiler will assume that we'll be calling a method that belongs to the static type, which is dog, or one of the parents of the static type. And because the static type is dog, and dog does not have a play method, the compiler will error. Okay, yeah, sorry. So for those of you on Zoom, the compiler does not have access to dynamic types at compile time. So because of that, the compiler, I don't know if you can hear me now better, but because the compiler looks only at the static types, when the compiler tries to access the play method within dog, it sees that there is no play method, so the compiler will error. So at compile time, Dristi, methods in the dynamic type are not available. The compiler does not see them. Only during runtime will the Java runtime environment see them.
Okay. That is a much better explanation, yeah. Okay, walking through the third question. So we have our PIM object. So when we call the play method, we look in the Poodle class for the play method. And one thing also to keep in mind is that pay attention to whatever the like type of the arguments is. Yeah, you can see like there's two different play methods here. The first one is calling a dog object and the second one is calling a poodle object. So in this case, because our argument is of the dog type, we're going to call this method right here and output no. And then similar object for the next call, we're calling the play method that takes a poodle argument. So we're going to print out bow wow. Okay, so the next thing is when we call, when we call the bark method on PIM, we can see that, my gosh, the first thing that we do when we call this method is that we look within the Poodle class and see if there's a bark method that takes a dog argument. There is over here, so we print out woof. And also one important thing is the reason that we override this method in the dog class is because the method in the dog class is not static. If it's not static, it means it can be overridden, so we use the implementation from the subclass. Okay, next thing, similar thing, again, like I think the main point of including like these different arguments is just to make sure that like the subtlety in the argument type isn't missed. Call the bark method in the poodle class. Argument is a poodle, so we output woof. Okay, so the next thing kind of like highlights what oh, he left, but it highlights what the other mentor was saying from before. So at runtime, basically, if we have an object that has different static and dynamic types, what we're doing here is when we call this method, we look within the superclass to see if we have an argument with the relevant signature. Okay, we can see over here that the bark class is overridden within the subclass, and because of that, we're gonna print out, sorry, we're gonna print out woof. It keeps doing that, sorry. I'm like trying to use the mouse.
What are you trying to do?
They said like earlier to try to use the mouse to like refer.
No worries. Yeah, then it will be hard. I think what we can do is
Okay, that's perfect, thank you. Okay, so the last method. So we take our dog object and we look in the dog class to see if we have a method that takes in a dog argument. We do, but the thing is, we have that overridden within the subclass here. We have a bark method that takes in a dog object, so because of that, we use the implementation from the subclass. And then, okay, for the last question. I'm so sorry, I'm completely blanking here. I don't think so.
So let me know again if you can't hear me properly for those on Zoom. So with dynamic method selection, when we do dan.barkpim, so what will happen is basically the compiler will see if there's a bark method within Dan's static type. So it sees that indeed there is a bark method within Dan's static type, which is dog. So it locks onto the bark method with that exact function signature. So if you pay attention to the function bark within dog, you'll see that function signature returns void and takes in a dog object. So when we move on to runtime, the Java runtime environment will specifically look for a method that takes in a dog object, even if there's a better method that takes in a poodle object, which is pim static type. So when we move on to runtime, right, the compiler saves this method, this bark dog d method, and then in runtime, when the runtime environment looks within Dan's dynamic type, which is poodle, for a bark method, it will look for one that takes in a dog. There is only one bark method that takes in a dog, so we'll print out wolf instead of printing out yap, which is what we might expect if the Java dynamic method selection system didn't work that way. But because we locked on to a specific function signature at compile time, we will use the bark dog d method within poodle instead of bark poodle p. Yes.
If there was a method that would work in the raw class that took in a poodle,
yes, it would use that one instead. Yes. Okay. Yeah. So if there was a bark method within the dog class that took in a poodle instead of a dog, the compiler will latch onto that method, and during runtime we will execute the bark poodle p method within the poodle class instead. Yes.
compile time when the parameter of bark in the dog class is like dog, does it not matter that you pass?
A poodle is a dog. The compiler sees that inheritance, so it will lock onto that bark method. Yes. So an example of a runtime error, I'm trying to think, there's a really good example I like to use that I forgot. I can think about that a bit more and then get back to you. Right. And then, yes. Yes, so the reason why it's yap and not wolf is because at compile time, when the compiler sees dan.barkpim, right, all it sees is Dan's static type, which is dog. So the compiler looks within the dog class for a bark method, and that takes in a poodle. It sees that there is no bark method that takes in a poodle, so it goes for the next best thing, which is a bark method that takes in a dog. Now the compiler latches onto that method, right? It saves that method, and it tells the runtime environment, when we eventually run this program, look for a bark method in poodle that takes in a dog. So I don't care if there's a better function signature, I want you to look for this specific function signature. So when we eventually run the program at runtime, the runtime environment looks within Dan's dynamic type, which is poodle, for specifically the bark dog D method, not a bark poodle P method, for example. And it sees that it's there within the poodle class, so it'll print wolf. Yes.
And if there was no bark dog D method within poodle, would it just go with bark then?
Yeah, so if there was no bark dog D method within poodle, we'll look in the parent class, and we'll see that there's a bark dog D method there, because the parent of a poodle is dog, so it will execute that method instead and print bark. Yes. Yeah, exactly. So the question was, why is number 3 no? That's because at compile time, Pim's static type is poodle. So the compiler will look within the poodle class, see that there's a play method. And in terms of which play method we use, we look at Dan's static type, not its dynamic type. So since Dan's static type is dog, we latch onto the play method that takes in a dog, not the one that takes in a poodle.
I actually have an example for a runtime error. So if you have the dynamic type being a superclass, whereas the static type is the subclass, remember how we said that the dynamic type is bound during runtime? If the compiler sees that the static type and dynamic type are not according to the rules at which we provided before, I believe that would be a runtime error.
So another common occurrence of runtime errors is whenever we deal with casting. So if you make an improper cast that works during compile time, well, actually, first of all, when you cast, you're basically telling the compiler to ignore any type errors. You're saying that this is the type that it'll be at runtime. If it turns out that you make an improper cast, that'll get past the compiler and it would manifest as a runtime error. So I think there are several example problems that do casting. I can find some and maybe include that in part of the ed post on 61B. Okay. All right, so we have to move on. I think we're asymptotics now. So is Kelly here? Okay. And if you have any further questions, we'll have some time during the break and after the presentation to ask more questions. Yes.
Do I press enter every single time?
You can press enter or you can press, oh dear. There we go. Yeah, so you can press.
Oh, okay, yeah. Okay, so we're gonna go over the asymptotics. So asymptotics are normally used to estimate the performance of our programs, and there are 3 types of bounds, which are big O, big omega, and big theta. And then our runtime Rn here is within the theta Fn, which means if there's like constant K1 and K2, our runtime should be within the bounds of K1 times Fn and K2 times Fn. So there are multiple types of orders. So first, the greatest one that takes like the most runtime is big O n factorial, followed by big O 2 to the nth power, n squared, n log n, big O n, big O log n, and then our constant bound, which is like big O 1, would be the fastest one. Okay, so whenever we're trying to solve the asymptotics problems, we are always assuming that our inputs grow large and approaches infinity. And even though we're trying to get the lower bound, we are always assuming, we are always considering the case when we have the infinitely large input values of n. So lower bound does not necessarily mean that the input size is small, but then the only thing we care is the property of the input, such as like array that contains all of 0 can be the lower bound, but then like input size can be like infinite numbers of 0. And then so upper bound does not necessarily mean the worst case, and lower bound does not necessarily mean the best case, because let's say the lower bound of the function is the big omega n, but that does not necessarily mean our best case is theta n, because our runtime of the best case can be larger than the lower bound, such as like it can be theta n log n, theta n squared, even though our lower bound of the function is big omega n. And then vice versa, even though our best case is big theta n squared, our lower bound can be like equal to that or smaller than that. So our lower bound can be like theta big omega 1, big omega log n, omega n squared. It can be like smaller than the best case. So there are multiple types of rules that you should write on the cheat sheet. For example, if there's like multiple inside the bound, if there's like a multiple orders, we only consider like the highest order. For example, if we have big O n squared plus n, since n squared is like highest order than n, we're only caring about n squared here. And then if there's any constants in front of the order, we can remove the constant. For example, if it's big O 100 n squared, we can just eliminate the constant, and then it will be it will be just big O n squared. And then we're always trying to get the tightest bound here. There are also summations that you should memorize. So first one is 1 plus 2 plus 3 plus all the way up to plus n. That sums up to n squared. And then n plus n over 2 plus n over 4 all the way up to plus 1, that sums up to n. So whenever you're adding up the numbers that increases by the constant, that always sums up to n. And then if you're trying to solve if the asymptotic problems contains the recursive, try to draw out the recursion tree, and then try to get the total amount of the work. Okay, so I'll give you guys like 2 minutes, 3 minutes. Oh, okay. And then try to read and solve this problem. Yeah. Oh, you can just consider it as constant. Run. Okay, does anyone want more time? All right, we can go over it together. So we're first looking at the if statement at the top, and then if n modulo 2 is equal to 0, the function will immediately return and it will stop. So this is our best case, which is theta 1, which is the constant time. And then for the worst case, we have to care about not only the if statement, we have to look at the for loop here. So let's try to summing up the runtime for each iteration. So notice how the for loop is starting from I equals 1, and then loops until like I is less than like n, and then I doubles every time, right? So our function will be h1 plus h2 plus h4 all the way up to like hn minus 2 plus hn. And then that sums up to like according to the rule of summation, that sums up to theta n. So that would be our worst case here. Any questions on this problem? Oh, sorry. It cannot be log of n because here we're like when we have this for loop, we are summing up the runtime for every single iteration, and then for each iteration our I value like doubles up, right? And then assuming our h is like takes constant, and then h1 is 1, h2 is 2, and then h is linear here. Oh, that's why. Oh, sorry. That makes more sense. Yeah. Yeah, so h takes the linear time, and then like h takes like different values of I, and then our I value like doubles up every single time. So if we sum up like every single cases of like every single iterations of I, that's basically like this sum, like 1 plus 2 plus 4, and then like if we sum up the constants that doubles up every time, that sums up to n. So that should be the theta n here.
What about the summation? Like, shouldn't that summation be like log n itself? And then it's like
What do you mean by the summation itself here? You mean the summation of like one? Uh-huh.
so like usually you execute the for loop log n times like the h of I, which is n, should be like n log n.
No, you're not. Oh, here you're not multiplying like the log n with n. So there are like log n terms. Like for example, like we're adding up like log n times. but then like if you add things up log n time, that will sum up to n here. Yeah, so we don't care about the terms here. Like we are summing up log n times, and if you sum up log n times, that eventually like sums up to n. Like we are only caring about the output value here. Any other questions? Okay, then we can move on to the next problem. Oh, okay. So let's go over this together. So we're trying to analyze the runtime for each part separately. So we are first looking at the if statement, for loop, and then another if statement. So the best case would be theta n. Okay, so this h takes a linear time. So hn would be like the runtime for hn would be n, and then like the best case is that our if statement returns like this case is true and it immediately returns. So our best case here would be theta n, and then for the worst. And then here for the worst case, we have to care about the for loop here. And then for the for loop, we sums up the runtime for each iteration. So here, our I again doubles up, and then we have another for loop inside, which takes j equals n minus I, and then it goes until like j less than n, and then j increments every single time. So in the outer for loop, our I value doubles every single time. So this would be another like 1 plus 2 plus 4 sums up to, which is like log n terms, and then all sums up to like n, theta n. So that's this for loop is another like runtime of n. And then this if statement returns if our n modulo 2 is not equal to 0. So that takes the constant time. So best case if we immediately return after this if statement, and our worst case is if we go through all this like all of these. So there would be n plus 1, which is 2n plus 1. But then according to our asymptotics rule, we're ignoring the constants and then the coefficient in front of n. So that would be also the theta n. Yeah. Mm-hmm. Oh, so our I value, like every single time it doubles, right? So that's outer for loop. And then like for the inner for loop, that's so our inner for loop depends on the I value here. So if our I is equal to 1, our j will like loop through like n minus 1, I mean like I minus 1, and then I doubles, right? So I increases from 1 to 2, 2 to 4, and like 4 to 8. So it increases 1, 2, 4, 8, and then like increases like with the constant. So for every single time it multiplies by 2. So our inner for loop depends on that. So our inner for loop like iterates 1 time, 2 times, 4 times, and then we're summing up like all the iterations here. Any other questions? Yeah. Oh, our best case is if we go through the first for loop here. So, but then if we want to go like, you can just think like we can just like go through the last for loop and then like it can be like theta 1. But then before this if statement, there's like a for loop we have to go through. So yeah, there's like a for loop before this if statement. So our best case would be just like the if statement here. Yeah. Big O and big omega, you mean? Oh, Oh, okay. So the best case, so that's our our upper bound we use big O, and our lower bound we use big omega. And then like for the best case and worst case is the theta bound of our so worst case would be our theta bound of our worst case, and then theta bound of our best like lower bound. So best case would be the theta bound of the lower bound, and then worst case would be the theta bound of the upper bound here. For example, yeah, the bounds are different. Any other questions? Okay, then
Okay, so I will be talking about the graph traversals, most importantly BFS and DFS. So first of all, let's start with reviewing some of the graph basics. That a basic graph has vertices, a set of vertices, a set of edges, and optionally edge weights. And graph can have like different variations. They can be directed or undirected. They can be cyclic or acyclic. And another property is that some graph can be connected and some can have like disconnected components. And I have like on the right some examples for us to go through. So I'll just give an example. The first one like on the topmost would be a graph with edge weights. And does anyone know what's the like how do we what's the next graph here if we want to classify it using directed, undirected, and stuff like that? Yeah. Yes. So this one is undirected and it's also, yeah, it has no edge weights and it's also not non-cyclic, acyclic. So the one on the right would be an example of directed and acyclic, and then on the bottom, it will just be directed and cyclic. And then going off from connected, we have this very special type of graph, which is connected, acyclic, and undirected graph would be a free tree. A free tree is just a tree that doesn't have a designated root. So then that's what we call a free tree. But for all of the trees, we have this very important property that the number of edges that it has equals the number of vertices minus 1. And that is because it's acyclic. Are we good over here? Okay. And then I'll just talk about some representation of graphs. In like actual implementations, we will represent the nodes with numbers and we'll use the numbers to represent the edges. So in order to represent the edges, the most common way and the most, I guess, the best way to implement that is to use an adjacency list. However, you can also use list of edges and adjacency matrix, but that would just be more, I guess, runtime wise, it will be O of V squared, comparing to adjacency list has a runtime of O of V plus E. Does anyone have any questions about this? Okay, and then we can talk about graph traversals. So first we'll be talking about DFS, which stands for depth first search. So for graph traversals like DFS and BFS, we don't care about edge weights. And for DFS, we use stack or we can use recursion. Basically, in DFS, we want to traverse our unvisited vertices as far as possible. And it's useful in questions like detecting connectivity or is there a path from the source to the target. So DFS is generalized from pre-order, in-order, and post-order traversals in tree traversals. Just as a refresher, pre-order in tree traversal goes from visiting the node to left and right child. And in order goes from the left child node, and then the right child, and post order goes from left, right, and visiting the node. And there is a trick to get the correct tree traversal orderings that I really like to use is to draw lines next to the node. So to break that in depth, it would be for in order, you would draw the line below the node. I don't know if I can use the whiteboard anywhere. Okay, I think I'll use the annotate. Yeah, okay. So it would be something like this. Sorry, it's really ugly. So if we have a basic BST that looks like 2, 1, oh, I see. All right, thank you. So it's 2, 1, and 3. Then a in order by what I mean by like drawing the line would be you draw a line like below the nodes. And then when you trace the BST, it will give you the correct ordering output in order. So it would go from 1 to 2 to 3. And then for post order, actually for pre-order, it would be a line from the left to the left of the node. And then in this case, you can see it gives us 2, 1, and 3. For post order, it's on the right of the node. So that will give us 1, 1, 3, and 2. So this is just some nice properties that will come in handy in the exercise questions that we have. Okay, then going to the next slide, I have this example of the running like pre-order and post-order on this graph over here. If we choose to break ties choosing the smaller neighbor, then for pre-order, we're going to start from the source and we're going to go to 1. Oh, we're going to immediately output because we visit the node first and then we visit its neighbor for pre-order. So we immediately output 0, and then we go to 1 and we output 1 and then we choose between 2 and 4, which are our 1's neighbor, but we choose 2 because we break ties choosing smaller neighbor. So we go to 2 and then we output that, and then following that we go to 5, and from 5's neighbor we choose to go to 4, and from 4's 4 only has 1 neighbor, so we go to 3 and then we backtrack from 3. 4 doesn't have any like unvisited neighbor, so we go back to 5, and 5 has 6, which is unvisited, so we go to 6, and then we go to 7, and then we backtrack from there, and finally we can go visit 5's last unvisited neighbor, which is 8. And then for post order, we also choose to break ties choosing the smaller neighbor. So we will start again from the source, which is 0, and then we go to, so for post order, we visit its neighbor first, and then we visit its node, right? So we start from 0, and then we go to 1, and from 1, we go to its smallest neighbor, which is 2, and then we go to 5, and 4, and 3, and notice at 3, it doesn't have any like untraversed neighbors. So that's the first node that we are going to output or visit the node. So following that, we backtrack from 3 and then we output 4 because we also visited all of 4's neighbor. So backtrack further from that, we go to 5, but we don't output that yet because we haven't visited 6 or 8. And you can like kind of follow that and get the following output. Does anyone have any questions about pre-order and post-order? Yeah. Yeah. So for trees, we can use pre-order, post-order, and also in order. But for graphs, we don't have in order because like in order requires us to traverse the left child first and then the node and then the right child. But for graphs, we don't know, like it can have as many neighbors as it wants, so we don't know where to put the, like visit the node, you know. Okay, yeah. And then another thing that we might want to notice in DFS is topological ordering or topological sort, which is just the reverse post ordering. And it works on a directed acyclic graph. So topological sort is useful if you have some intrinsic like ordering in the graph, and then you want to output it as like a sequence that you can follow, that just goes from like the lowest, I guess, significance to the highest. Like you can lay it out as a sequence of directed links. Okay, and then the next thing that we are going to talk about is BFS. So similar to DFS, we don't care about edge weights, and here we're using Q as our fringe, rather than stack or like recursion in DFS. And then we traverse unvisited vertices based on the number of vertices from the source vertex. So BFS is especially useful in questions like find the shortest path between the source and the target. And it is generalized from level order traversals in tree traversals. So similar as like before, if we look at this example, then you can see we first output 0 because it's the source vertex, and 1 because it's one edge away from 0, and 2, 4, which are both 2 edges away from 0. And you can kind of follow that same logic. Okay, so then we'll talk about runtime before we dive into the question. So both DFS and BFS has a runtime of O, V plus E, V being the number of vertices and E being the number of edges. And that is because we traverse each edge at most twice. And each traverse, which just means that we're pushing into the stack or the queue, takes constant time. And we visit each node at most once, and each visit, which just means popping from the stack or the queue, takes constant time as well. So a pro for BFS and DFS traversal would be really fast runtime, but a con would be that it doesn't care about edge weights. So we can't use it to find like actual shortest path in real life. Like for example, Google Maps, we're trying to determine how to get from location A to B in the fastest way possible. Okay, and if nobody has any questions, we will dive into this question, this past exam from spring 2020. So the first question asks for the pre-order DFS traversal. If you guys want to take 1 minute or two to think about it. Okay, because of time constraint, we're gonna go into this question. Does anyone have a solution that they would like to share with everyone, with all of us? Okay, I can just go over it. So our source our source verdicts is node 4, right? So we're starting from node 4, and we immediately visit node because pay attention that we're doing pre-order here, and the order goes visit node and visit its neighbor. So we output 4, and then we go to its smallest neighbor, which is 2, and then we immediately output 2. And then after that, we go to 1 because 1 is 2's smallest neighbor. So then we go to 1, and 1 doesn't have any neighbor. Oh, sorry. We go to 1 and then we output 1. Or we add 1 to our output. And from here, since 1 doesn't have any neighbors, so we backtrack and go back to 2, and we see that 2 has a unvisited neighbor, which is uh, 5. And then we go back to and then so we visit 5, and then we go back to 2, and that's when we finished traversing all of the neighbors of 2, and that's when we backtrack to go to 4, and we see that 4 has a unvisited neighbor, which is 3. So the final output will be 4, 2, 1, 5, 3. If nobody has any questions, then I'll give you 1 minute for the post order. All right. Does anyone have a solution that they would like to share? Or just like any thoughts? So I think like a starting point to notice that this time we're starting from node 2, and it's actually kind of tricky. And after we have that observation, we're noticing that also we're doing post order, so we're visiting its neighbor first, and then we're visiting the node. So starting from 2, we're going to visit its smallest neighbor, which is 1, and we notice that 1 doesn't have any neighbors, so that's when we visit 1, and then we add that into our output. So backtracking from 1, we go back to 2, and we see that it has unvisited neighbors, which is 4. So we go to 4, and 4 has another unvisited neighbor, which is 3. And then finally at 3 is another like node that doesn't have any neighbors. So we put 3 into our output, and then we backtrack from there. And then we see that we exhausted all of 4's neighbor as well. So we put 4 into the output, and then we go back to 2, and notice that 2 still has another untraversed neighbor, which is 5. And then at 5, we put 5 into the output, and then finally we go back to 2 again and add that into our output. So the order will go as 1, 3, 4, 5, 2. Does anyone have any question about pre-order and post-order? All right. I think this next part is like the interesting part of this question. So this question talks about a pre a new kind of traversal, which is pre/in order traversal. Basically that in this new traversal, each vertex is visited exactly twice, and that's following first in the pre-order traversal order, like before we visit the left and right child, and then second time that we visit the node is in the in order traversal order, which is between left and right, when we visit the left and right child. So if you guys want to take 2 minutes to take a look at our past part C. Oh, okay. Due to like time constraints, I'll just go over it. So I think this question, like we can definitely follow the algorithm and notice that we are printing. So if we're starting from 1, then we're first printing 1 and we go to its left child. And when we're at its left child, we immediately print it as well, which is just the characteristic of pre-order traversal, right? And then after that, we can just kind of follow the algorithm, and that gives us a valid output. But another way that I like to think about is using the drawing line trick that I talked about before. So notice that we're asking for pre and in order traversal, so we can just add like this line to the left of every node, because that's for pre-order traversal. And for in-order traversal, we're adding a line to the bottom of the nodes, right? So we also add a line to the bottom of the nodes, of every node. And then if we just trace it, if we trace the graph, it will give us the correct output. Sorry, this is very ugly, but it goes like 1, 2, 5, 5 again, and then 2, 4, 3, 3, 4, 1. So that is kind of like a faster trick to get this question. Does anyone have any questions about part C?
The line down is
Yes. So I'd like to like point us to look at another observation which will help us in the later parts. So notice that between 2 and 2, which occurred here and here, we have like 2 5s, right? And that just means that this 5 is to the left of the 2, because we're going in this order, and you see that between the two print statement is whatever that is to the left of the node. So that is an observation that we would like to make in order for us to do the later parts. Oh, okay. Yeah. I encourage you guys to look at the questions.
Sorry, we're out of time, but we will release the slides. So if you want to, you can go over this on your own time, or you can ask them. You ask a question about this at the end of the session. But we need to move on to our next topic, and that's. Oh, come on.
Yeah. So wait, like actually, I'll do this.
You can.
Okay, just do that. Okay.
Yeah. First.
Okay. Okay. All right. Hi. So our next topic is going to be on BSTs. So we're going to be going through 2 free trees as well as left leaning right black trees. How to insert into each of these, and we're going to go through a couple of exam questions. So first, what are 2 free trees? There's a quick overview and review. The problem that we're trying to solve with 2 free trees is that BSTs are great. They're ideally very fast for insertion, deletion, and searching. Problems that sometimes they become twiggy, and the leaves aren't on the same level. For example, if we insert 5, 2, 6, 8, 9 to a BST, we get this. You can see here that like trying to locate 9 will take longer than trying to locate 2, because 9 is on a whole different level compared to 2. It's distance 3 from 5 compared to 2, which is distance 1. And if we continue to insert more and more larger numbers into this BST, that will eventually cause us to essentially create a linked list, which sucks. That then gives us asymptotics of theta n, which is bad. So we're trying to solve this problem with 2 free trees, right? Because if we convert this BST into its equivalent in 2 free trees, we can see that we get this pretty beautiful 2 free tree that ensures that all leaf nodes are the same distance away from this root. So 2 free trees are special because of this one property, is that all of the leaves must be the same distance away from the root. The way to do this is through 2 other rules. So leaf nodes can have 1 or 2 items, and all non-leaf nodes must take on one of the 2 following forms. On the left, you have the form 1. We've got Wait, where's the tool for like is this spotlight? Oh yeah, the pointer, exactly. Yeah, perfect. Yeah. So on the left here, you can see here, this is the case 1 where the parent has 1 item and there's 2 children. Case 2 is when the parent has 2 items and 3 children. And this is where the name 2 free tree comes from. Non-leaf nodes can have either 2 children or 3 children. The rules for these 2 cases are here. So in the first case, children on the left of our parent node must be less than the item within the parent node. Children on the right must be greater than the item in the parent node. In case 2, children on the left must be lesser than item 1, so 2 is lesser than 5. Children in the middle must be between item 1 and 2. 6 is bigger than 5 and less than 8. And lastly, children on the right are greater than item 2. So now let's just go for insertion. Any questions so far on 2 free trees? Good. Okay. So our goal is to insert 13 into this huge 2 free tree. So step 1 is straightforward. We insert the value into root and we follow the same rules as in BSTs and we go down until we reach the correct leaf node. So 13 is between 10 and 25. So we go through the middle child. 13 is less than 14 in the middle child, so we go to the left. And now 13 is greater than 12, so we put 13 into this leaf node after 12. Leaf nodes can have 2 items, so this is a perfectly valid 2 free tree, and we're done. The next rule is if we're inserting a value into a node and that results in a free item node, that's illegal because this is a 2 free tree. We can have at most 1 or 2 items within a leaf node. So therefore, if that happens, we have to push the middle value up and split the left and right items into new nodes. So let's give an example right now. Let's try to insert 28 into this 2 free tree, and feel free to just like look at this and try to do the same thing and like follow along with me. 28 is greater than 25 in the root node, so therefore we go to the right. 28 is less than 30, so we go to the left child. 28 is between 27 and 29, so we insert it in the middle of this leaf node. And oh no, we have a free item node. And this is illegal, so therefore we have to use rule 2 to push the middle value up and split left and right items into new nodes. So here the middle value is 28. So therefore we push 28 up into our parent node 30, and then we split our old leaf node into 2 different leaf nodes, like fuss, and boom, we now have another valid 2 free tree. The last case is a special case where we push a middle value up, and that node that we're pushing into becomes a free item node as well. What do we do then? Let's try to insert 11, and we'll see this go into play. So 11 is less than 10, more than 10, less than 25, so it goes to the middle node. 11 is less than 14, so it goes to the left. And so 11 goes into this leaf node. So therefore, now there's a free item leaf node here. We have to push the middle node, middle value up. We put 12 into the node above, and now we have another free item node again. And this creates a very interesting situation where after we split the leaf nodes, we have this like monster node with 3 items and 4 children. So what do we do? Well, first we do the same things that we did to the middle node. We push the middle value up because right now this node has 3 items, and that's bad. So we push the middle value up into our parent node. And now what we do is we take the left split node, so 12, and that inherits the leftmost 2 children. And then the right split node, 16, inherits the rightmost 2 children. You see here, basically, before the split, 12 takes the leftmost 2 nodes, and 16 takes the rightmost 2 nodes, like this. And lastly, we follow the same rules for our parent node. We move the middle up into a new node, and we split our node again. And here, the same thing happened again. We have 4 children as well as 2 about to split nodes. So the left split node takes the 2 children on the left, and the right split node takes the 2 children on the right. And now we have another 2 free tree. You can see here, even though we've added 3 more items, we all leaf nodes are still the exact same distance from the parent. Sorry, from the root. So runtime on 2 free trees are always theta log n. Because of the rule that leaf nodes are always the same distance from the root, the asymptotics for insertion, search, as well as deletion must always be theta log n. All right, next, red black trees. So the problem is that two-free trees are hard to implement in code because they're usually inefficient and it's hard to maintain different sort of nodes within Java. So therefore, we solve this problem by using red-black trees, which are exactly the same as two-free trees, just a different way to represent them, and easier to implement in code. For example, if we have a two-item node within a two-free tree, this is how we represent it within a red-black tree. We simply have the right node as the parent, a left-leaning red link to a child, which is 5. So this is the equivalent of a two-item node in two-free tree in a red-black tree. A bigger example is here. We have the two-free tree on the left and the red-black tree is on the right. A easier way to visualize this and figure out why it's represented this way is for us to actually take the red links and visualize them as connectors and to sort of like rearrange this so that the red links are horizontal. So you can see here, red links are basically connectors that represents the link between two items within the same node. So 5 and 8 are separate nodes on the right in the red-black tree, but the red link sort of represents 5 and 8 being in the same node within a two-free tree. Same thing for 9 and 10. 9 and 10 are two different individual nodes within the red-black tree. Because of this red connector node, red connector link, this essentially represents the 9 and 10 being merged together within a two-free tree. So yeah. Here are the properties of red-black trees. First of all, there is always a one-on-one correspondence with a two-free tree for a red-black tree. So if you have a red-black tree, you can always make one unique two-free tree from that red-black tree. 2, nodes cannot have two red links because if we have two red links, that basically means that we're merging free nodes together. So as you can see here, if we have like a node with two red links on the right, that will result in the free item two free tree on the left. That's illegal because that's free items, and we have at max 2 items within two free trees. Every path from the root to the leaf in a red-black tree must contain the same number of black links. Remember the same rule in two free trees is where all leaves have to be the same distance from the root. This is this equivalent within the red-black trees. Red links don't really count because they're kind of like merging like horizontally between two nodes. Okay, so what we do is we count the black links from the root to each leaf. So you see here, 7, 14, and 28 all go through only one black link going towards the root. And lastly, red links must be left-leaning. Because we're using left-leaning red-black trees, we cannot have right-leaning red links. So therefore, this is illegal. We can't have 5, 8, where 8 is to the right of 5. Questions so far? Great. Okay, so let us jump into some existing questions into red-black trees. Okay, so the algorithm for red-black trees insertion is the same as the BST. We basically follow the same rules as BST, and then we connect it with a red link after finding out where the new node should go. And here I've created a one-on-one correspondence where on the left we have the red-black tree, on the middle is like the horizontal representation of the red-black tree, on the right is the two free tree version of the red-black tree. Okay, so here let's try to insert free. Free is less than 25, so we go to the left. It's less than 10, so we go to the left. It's less than 7, so we go to the left. And now we've figured out where it should go. It should go to the left of 7. So we then link free to the left of 7 with a red link. And this is a totally valid red-black tree and a two free tree. You can see here that the equivalent of this red-black tree is this two free tree on the right. This is perfectly valid. We have 2 items per node, and each leaf node is exactly 1 distance away from the root. However, there are some possible problems that can arise when we're inserting new nodes into red-black trees, right? So we've got the double red link problem, the right red link problem, and the consecutive left red links problem. I'm going to go through each of these as well as what the cascading balance problems that y'all saw in lecture. So first of all, why is double red links a problem? Well, we saw before that this leads to essentially a free item node back in our two free tree version, and that's bad. Right red links are honestly it's actually okay. Like this is actually like valid in two free trees, but because we're using left-leaning red-black trees, this is illegal by the definition of left-leaning red-black trees. So even though the one-on-one correspondence is fine, like this is a valid two free tree, we cannot have right red links because we're using left-leaning red-black trees. And lastly, we have consecutive left red links where G and F are connected by red link, F and E are also connected by red link. And that's bad because that means that they're merged together, and this creates a free item node in the 2-3 tree correspondence. To deal with the first problem, double red link, what we do is we invert the colors of the parent node that has the 2 double red links. So in here, we invert the colors of node C. This is a tricky part. Remember that you need to invert the colors of both the children as well as the link connecting our node to its parent. So here, C to A and D becomes black, and C to G becomes red. And now the new correspondence is like this. And this is a perfectly valid 2-3 tree. So we've solved that problem. For the right red link, it's a little bit more complicated. We have to rotate left on the node that is the parent. So here we have to rotate left on C. A good way to visualize how to rotate nodes is to merge the child into the parent first, and then move the parent to the left of the child, basically. Our goal here is we want to take E, which is the right child of C, and make C the left child of E. So first, we take E, we merge it with C, okay, and we must keep the red line as a reminder that they're connected with a red link. And then we move C to the left and down of this merged node. And this creates this. And now this is valid because it has a left leading red link. Lastly, we have the problem of a consecutive left red links. In this case, what we do is we use the rotate right method on the parent on the most parent node that has the 2 red links. So here we run rotate right on G, which means that F is the left child of G, and want to make G the right child of F. So therefore, what we do is, again, we merge F and G together, okay? And we keep the red line to remind ourselves that they're connected by a red link. And then we move G to the right and down of F. Now, oh no, there's another problem. We've now caused a new problem where we have problem 1 within a red black tree. We have double red links. And this is very common when you're doing red black tree problems. Like solving one problem leads to another problem. So therefore, we now have to run our invert colors on our new red black tree to solve this problem. So we run red black tree. So we run invert colors on F, which then results in this. And this looks better, but now we have the right red link problem because C and F has a red link, and that's bad. We don't want red links to the right of a node. So therefore, we have to run rotate right. Sorry, wait. I should say rotate left. Sorry, rotate left on C. Okay, so that F is now the new parent, and C is to the left of F. So therefore, we merge F with C, and then we move C to the left and down of F, which then causes us to have a perfectly fine and valid 2-3 tree. So yeah. So let's go for some questions now. Okay, we have a 2-3 tree on the left. I'm gonna give you guys 2 minutes for you guys to convert this into a valid left leading right black tree. Okay. A big tip that I have is to use the horizontal red link trick in order to visualize how red links create 2 item nodes within 2-3 trees. Okay, all right, due to time constraints, we're gonna go ahead and start it. So I'm gonna go through from the top to bottom how we convert this. So first we have the 2-item node at the top. So therefore we use a red link to represent this with 10 and 40. We then represent the second sort of level like this, where 5 and 8 are connected with a red link to represent the 2-item node. 15 is to the right of 10, and 90 to the right of 40. And then lastly, for the last level, looks like this, where basically we have 3 and 6 to the right of to the right, 9 to the right of 8, 20 and 30. The 2-item node is connected with a red link there, and yeah. And then after we sort of like we can like reorganize this a little bit, get rid of like the horizontal lines, and this is how it looks like in red black. Yeah. I'll give you guys a little bit of time to like look at this and compare it to your answer. Yeah. Any questions? Great. Okay, so last question is going to be questions on rotations. Okay, so our goal here is we have a BST, and we want the new root of this BST to be the node contained integer 10. So we're taking this node 10, trying to move it to the parent. The root of this entire tree. Okay, and we can do this with 3 rotation operations on this BST. So fill in the following with the type of rotation and item in the BST node to be rotated. Due to time constraints, I'm just gonna go through this question with you guys. Okay, remember that rotate left works like this. Let x be the right child of n and make n the left child of x. This is confusing, so I'm gonna label these terms onto the tree. So the first step is we want to rotate left on node 9. So therefore we assign n to the node 9 and we assign x to the node 10. So now we want to make n the left child of x. So we merge 10 with 9, and then we move 9 to the bottom left of 10. So therefore, it becomes like this. Next, we want to kind of swap the positions of 10 and 11, right? So therefore, we use rotate right on 11. We assign x to 10 and n to 11. We want to make n the right child of x. So we merge 10 with 11, and we put 11 to the right and bottom of 10. And creates this. And lastly, we want to rotate left on 5. We assign x to 10 and n to 5. And then we make 10 the new left child of 5. Sorry, we make 5 the new left child of x, which results in this. And now 10 is the root of the entire BST. Questions? Great. Okay, I'm done.
All right, guys, thank you. That concludes the first half of our final review. You're going to have a 5-minute break and then hop into some more topics. Thank you for sticking around.
Yeah, I know. It's so cool. What's their first?
You might be interested in doing that. There's only two of them. Raise your hand if you would like a candy. Right, candy cane. Warhead. Oh, another warhead. More warhead. The rubber duck.
Hello?
Right now? The break ended? All right, the break is over. Let's now go over the sorting. Okay, so our next topic is comparison sorts. So I'm gonna explain about selection sort, insertion sort, quick sort, merge sort, and heap sort, and then let's go over this problem as we go over these sortings. So the selection sort is that we first search for the smallest element. So we start at the left and then like go through the list, go through the array, and then find for the smallest element. In this case would be 1 here. And then after we found out the smallest element, which is 1, we swap this first element with the smallest element. So in this case, we will swap the location of 4, which is the first, and then 1, which is the smallest one. So that's after we swap the location of 1 and 4. And then, so 1 here is sorted. And then after 1, it's like 5, 3, 2, 4, this is the unsorted part. So we're going to repeat this until until this array is like completely sorted. So next up, we're going to start at 5 and then look for the smallest element, which is 2, and then swap the location of 2 and 5, since 5 is the first element within the unsorted part. Okay, so this was the example for fall 2020 final exam. And then, so in this case, we're also gonna start from the left and then search for the smallest element. In this case would be 1. So our first swap was swap 1 with the first element, which is 4. So in this case, after the first swap, it will be 1, 5, 4, 2, 3, 7. Any questions here? Right, and next up is insertion sort. So insertion sort, so at the first, the whole array is unsorted, and we swap to the sorted part if necessary. So what it means is that, 4, so our first element is 4, and then 4 is just 4. So this 4 is sorted part, and then 5, 3, 2, 1 is unsorted part. Next up is 5, and then since 5 is greater than 4 and it's located right side of the 4, this is sorted, this is right. So we just keep it as 4, 5, and our 3, 2, 1 is our unsorted part. And we're going to repeat the same process until the whole array is completely sorted. So our next up is 3, and since 3 is less than 4 and 5, we're going to swap 3 to the front twice. So after we swap 3, it will be 3, 4, 5, where these 3 are sorted, and then 2, 1 would be the unsorted part. Okay, so our best case here would be the case when our array is already completely sorted. In that case, if our array is completely sorted, we're just gonna go through the list with whether it's already sorted or not. So our best case, the runtime for the best case would be the length of the array, which is n. So it would be theta n. And then the worst case would be this case, like 5, 4, 3, 2, 1. If it's like completely like in the reverse order, in that case, we're gonna have to swap the numbers, and then not only swap the numbers, but also to go over like the array from the start to the end. So it would have runtime of n squared. Okay, so I'm gonna give you guys like 1 minute to think about like the first swap, if it's like the insertion sort. Okay, so this is insertion sort. So we're gonna start at the left, so and look for the smallest element. So 4, 5, 1, 2, 3, 7, and 1 is our smallest element. So we're gonna oh wait, that's selection sort. So starting from 4, 4 is just 4, and then next up is 5. So 5 is greater than 4. 5 is greater than 4, so this is right. So this is sorted. But then if we go to 1, 1 is smaller than 4 and 5. So we're gonna swap the location of 1 to the left twice. So sorry. So it would sorry. So it would swap the location of 5 and 1 first. So it would be 4, 1, 5, 2, 3, 7. And then since 1 is like still smaller than 4, it will swap the location of 4 and 1. So at the end, it will be 1, 4, 5, 2, 3, 7. Any questions here? Right, then let's go over the quick sort. So quick sort, we first have to pick our pivot. So in this case, we're just gonna assume that our pivot is the leftmost item, which is 4 in this case. And then after we pick our pivot, we're just gonna move all the items that's smaller than the pivot to the left, and then items that's greater than pivot to the right. So in this case, since 3 to 1, these 3 are less than the pivot, which is 4, it would move to the left side of the 4. We're just gonna move them to the left side, and then 5 is greater than 4, so we're gonna move to the right side of the 4. So 4 is our pivot, and then we're gonna run quicksort again between 3, 2, and 1, and then 5 until like this array is like completely sorted. Okay, so in this case, again, our pivot is 4, which is the leftmost number. And then our left pivot stops at the value that's greater than pivot. So 4, so starting from the right, we're gonna go to 5, and 5 is greater than 4. So this would be our left pointer. And then our right pointer would start from here to the right. And then since 1 is smaller than 4, so 1 would be our right pointer. And then we're gonna so when the both pointer stops, we're just gonna swap the value between that, and then yeah, so we're just gonna like start from the left. So left pointer start from the left, right pointer start from the right, and then like when the pointer when the left pointer cross the right pointer, that's when we're gonna swap the pivot with the right pointer. So I'll give you guys like 1 to 2 minutes to think about this. Okay, anyone want more time? Okay, so in this case, so we're again choosing the leftmost element as our pivot, which is 4, and then starting from the left, our left pivot should be the greater than 4, so which is 5. We stop at 5 here, and then starting from right, our right pivot. So since 7 is greater than 4, we move to the 3, and since 3 is less than 3, we stops here, and then we will first swap the location between 5 and 3 here. So that would be our first swap. Any questions here? Okay. So our next up is merge sort. So merge sort, and for merge sort, we split the array into 2 parts, and then we're gonna like again run merge sort between these 2 and these 3, and then And then after we're done like dividing this into two, we're gonna merge them together in the correct order. And that's gonna take the total of n log n. And log n is coming from like we're splitting the array two parts like recursively. And then our heap sort. So for heap sort, the key thing is like we have to make the array so into like max heap form. So we first have to bubble down in reverse level order. So we're first gonna heapify the array into the max heap. So in this case, in this example, since 5 is greater than 4, we have to swap the location between 4 and 5 to make it into the max heap form. So after we made the array into the max heap form, we have to we first pop off the first element, which is 5, and then swap it with the rightmost unsorted element. In this case would be 1. So after that, so 5 just move to the rightmost part of the array. So in this case would be 4, 2, 3, 1, 5 after popping off the first element. In this case 5 is sorted, and then 4, 2, 3, 1 is unsorted part of the array. So in our tree, 5 is now gone. We have 4, 2, 3, 1. And then after that, we have to make it into the maxi form again. So since 1 is smaller than 4 and 2, we have to like move 1 down twice and to make it into the maxi form here. And then after we move 1 down, and we have to like pop up 4 in this case and move to the right side of the unsorted array, and then repeat the same thing until the array is completely sorted. Yeah, so our best case here would be like theta n, and the worst case here would be theta n log n. Best case coming from like if it's like already like in the maxive form, then we just have to like go through the array that's coming from the theta n, and our worst case is that we have to like heapify the whole array again, and then like just put the first element to the last, and then like keep doing that until the array is completely sorted. Yeah, so again, this is example from fall 2020. I'll give you guys like 1 to 2 minutes to think about the first swap. All right, let's go over them together. So our first swap would be between 1 and 7, which is like our first goal is to heapify the array to make it into the max heap. and then 1 is more than 7, so 1 have to go down, and then like 7 have to go up, and then eventually like 7 would be at the topmost because like 7 is the greatest if we after we simplify the array. So our first swap would be 1 between 1 and 7. Any questions? Right, then
All right, we will now go over shortest paths, basically Dijkstra's and A star. So in Dijkstra's algorithm, we are given a graph and a starting vertex. And what we want to do is that we want to find the shortest path from our start vertex to all other vertices in the graph. Now, how exactly does Dijkstra's algorithm do this? So what we do is that we first create a fringe and some other stuff we'll need in our algorithm. We initialize all of our vertices to have infinite distance from our start and to have nothing as their parent. And now we actually begin to run the algorithm. So we set the distance of our start vertex to 0, and then we place all of our vertices into our priority queue. So note that at this stage, when we have our mappings in our priority queue, only our start vertex will have a distance that is 0. Now, while we still have items in our priority queue, we remove the vertex with the smallest distance from our priority queue. And then once we have this minimum distance node, we loop through all of its neighbors and we check, is their current distance that we know of greater than or less than the distance of our current node plus the weight of the edge connecting our two edges. If distance of our current node plus the weight of their connecting edge is less than the neighboring node's distance, then we replace that distance with distance u plus weight uv, and then we change the parent of that particular neighboring node in our table to be our current node, and then we update the priority of that neighboring node in our priority queue. So for example, if we're at our starting node, which has distance 0, then since we have a min priority queue, our starting node will be the first node popped off of our priority queue. And now we take our starting node and we check all of its neighbors and we update everything accordingly. So now this begs the question, what exactly is the runtime of Dijkstra's algorithm? So if we take a look through our algorithm, we'll see that we'll have v calls to add, where v is the number of vertices in our graph. And we'll have at most OE calls to change priority, because we'll be changing the priority of various vertices at most the number of edges in the graph. Similarly, we'll be popping off nodes from our priority queue at most OV times. Now, a min priority queue can do each of these actions in O log V time. This does not necessarily hold true if we are not using a min priority queue to implement Dijkstra's. And sometimes Dijkstra's implemented with other data structures will show up on exams, so try to keep careful note of this. Now we'll get some conceptual practice with Dijkstra's. So here we have 3 true or false questions regarding shortest paths trees. Now assume that all edge weights are positive unless otherwise stated. The fact that the edges are positive will be very important. And I will give you guys a minute or two to think about these questions. All right, in the interest of time, let's start going over these questions. So first up, we have this statement. Adding some positive constant to each edge in the graph does not affect the shortest paths tree. This statement is false. Now, why is it false? So let's say we have a graph with 3 vertices, and we have two different shortest paths. For example, one shortest path, or like not really shortest path, but let's just say it's a path. One of the paths through our graph has 2 edges in it, and the other path has 1 edge in it. And now let's add our positive constant, let's say 2, to each edge. We'll see that the path containing 2 edges will have its total weight updated by 4, whereas the path with only 1 edge will only have its total weight updated by 2. So we can see that, let's say we have a graph with vertices A, B, and C, and we are finding the path to all other vertices in the graph starting at A. So if A to B is 2, B to C is 4, and then A to C is 7, and we add 2 to each edge. Originally, our shortest path will be of total weight 6 going through A, B, C. But after we add weight 2 to every single edge, then our original shortest path will no longer be our shortest path. Our shortest path after 2 is added to each edge will now be going directly from A to C. So if we're adding a positive constant to each edge in a graph, then it disproportionately impacts paths that use more edges. All right, so now let's look at our second statement. Multiplying each edge in a graph by some positive constant does not affect the shortest paths tree. This statement is true. Why is it true? Let's say that our shortest path has weight W0, and we number all other possible paths in our graph, all other possible longer paths in our graph to be W1, W2 through Wi, and we multiply each edge by some positive constant k. The total weight of our path will now be kW0, kW1, so on, kwi. Our shortest path will still be our shortest path. It's just that its weight will be some proportional constant k to its original weight. Now on to our third statement. Running Dijkstra's on a graph with negative edges never returns the correct shortest paths tree. This statement is false. Now let's quickly go over why Dijkstra's does not work on graphs with negative edges. So when we pop a node off of our min priority queue, Dijkstra's assumes that the distance to this particular node is the shortest possible in our graph. But what if we have a negative edge later on? That negative edge could decrease the path to that node. So the shortest path to that node isn't actually the one found by Dijkstra's. But why does Dijkstra's return the correct shortest path tree if all negative edges are adjacent to our starting vertex? Well, Dijkstra's will check all these negative edges. So there's no possibility that the shortest path to any particular node can decrease later on. They can only increase because all the other edges in the graph are positive. All right, now let's quickly go over A-star. So A-star search is very, very similar to Dijkstra's, except that it has a slightly different goal. Rather than finding the shortest path to all other vertices in a graph, we're now only looking for the shortest path to one particular vertex in our graph. And now we also have the help of something known as a heuristic to help us in this goal. A heuristic estimates the distance from our current node to our goal node. And now when we're looking at vertices in our fringe, instead of putting in just their distance, we now put in the sum of their distance and the heuristic value. And when we're going through our A-star search, once we reach our goal vertex, then we know we are done. We no longer need to go through any more edges or vertices in our graph. Now, in order for A-star to return a correct path through our graph, there are 2 requirements that our heuristic must meet. First of all, our heuristic must be admissible. What admissible means in the context of A-star is that the heuristic cannot overestimate the actual distance to our target node. So let's say the distance to our target node is 5, and that means our heuristic value cannot be greater than 5, or else our A-star search will be invalid. Similarly, a heuristic must also be consistent. Basically, the difference in heuristic value between two vertices cannot exceed the difference in actual distances from the goal vertex. The summary here is that our heuristic can never overestimate the actual distance. So now we'll do a practice problem involving A-star. Yes. So we can use, so let's take a look at our table right here. So let's see that we have a heuristic value of 2 attached to vertex A, a heuristic value of 2 attached to B. And basically what these values do is that we're looking for our shortest path to G. So what H of A is saying is that it estimates A to be distance 2 away from G. And vertex B is distance 2 away from G, and so on. Does that answer your question? Any other questions? Okay, then I'll give you guys a few minutes to work on this question. And note that once again, this is A-star search, so the value we put into our fringe is a little different from the distance. In the interest of time, I'll start going over this problem right now. So we are given that we are trying to run A-star, and we're trying to find the shortest path from our starting vertex A to our end vertex G. So now let's put A into our fringe. So A is of distance A from itself, but it has a heuristic value of 2. So when we put the vertices into our fringe, then we'll notice that A gets put in with a value of 2. And now we look at the neighbors of A. We see that A has an edge going to B with weight 1 and an edge going to edge D with a weight of 5. So we update these values and put them into the fringe. And note that the value of B is 3 in the fringe because the heuristic value at B is 2. So 1 plus 2 is 3. And similar applies for vertex D. And then we continue this. We see that B has the highest priority in our min priority queue because its distance is the lowest. So we pop it off. And we once again update the values of the neighbors of B. So B has edges going to C and H. So these values get updated and put into our fringe. And then next we visit D, and then we continually repeat this, D, H, and G. And we see that we have popped G off of our fringe. G is the node that we want to visit. So we know that we're done with our A-star search and we can terminate. So we've visited nodes A, B, D, H, and G in our process. But here's where you have to be kind of careful. Note that vertex D is not actually along our path. But when we're returning our values, we only want the nodes that are along our path from A to G. So we do not want to include node D in this. So our final path is A, B, H, and G. Now there's one final question we should think to ourselves. Is our heuristic admissible? I will let you guys think about that real quick. It turns out that our heuristic is not admissible. So recall from earlier that in order for our heuristic to be admissible, it can never overestimate the distance from a particular node to the end vertex. But if we take a look through our heuristics, we see that the heuristic estimates for nodes for vertex C that it is distance 20 away from G. But if we take a look at our graph, we can see that vertex C is only distance 4 away from G. So our heuristic overestimates this distance, which means that our heuristic is not admissible, and therefore the path found by A star may not be correct. And in this case, you'll find that the path found by our A star algorithm is not actually correct.
Can you hear me? Yeah, now we'll be going over minimum spanning trees and the Kruskal's and Prim's algorithm. So yeah, so the first thing is, what is a spanning tree? So spanning trees are defined for undirected graphs only, and they're basically a subgraph of the original graph, and it's fully connected, which means that no pieces are disjoint. It's also acyclic, which means that there aren't any cycles. And just as a refresher, if you start at a vertex in a graph and you find a path that can cycle back to that vertex, that's not a cycle. And so these properties make a tree. Trees also have V-1 edges, where V is the number of vertexes in the graph. And lastly, the spanning tree contains every single vertex of the original graph, and that's where we get the spanning term from. So a minimum spanning tree is special because it minimizes the overall edge weight. And what that means is, if you add up the edge weights of the entire minimum spanning tree, we want that number to be like as small as possible. And so just as an example, if you had a bunch of houses in a neighborhood and you're trying to set up a network across it, we would use like an MST to figure out how to minimize the overall cost while connecting every house. And MSTs are actually used to design different types of networks. Yeah, so if you can see that this connects every single house in the neighborhood, and we've minimized the cost. Oh. Can you hear me now? Is this better?
Are you talking a bit loudly?
Can you hear me now? Okay.
So just talk.
Okay. Yeah, okay, so there's two types of algorithms that find minimum spanning trees that you need to be familiar with. And what we're going to be using for these algorithms is called the cut property. Wait, sorry. This slide isn't changing. Yeah, okay. Okay, so what the cut property does is we have a graph and we're going to split it into two groups by drawing a cut across the edges. And as you can see over here, the cut over here separates the vertices into gray and white. And so a crossing edge is one that lies across the cut. And what that means is it connects vertices from both sets. So one vertex is gray, the other is white. And so what the cut property does is that it basically tells us that out of all of these highlighted edges, the one with the least weight is going to be in the minimum spanning tree. And so just as a reminder, there can be more than one minimum spanning tree for a graph if you have edge weights which are equal in magnitude. Okay, so we're going to take a look at the algorithms that we use to find minimum spanning trees. And the first one is Kruskal's. So the main idea behind Kruskal's algorithm is to order all the edges of the graph in increasing order and then keep adding those edges onto the minimum spanning tree unless a cycle is created. And the data structure that we use in this algorithm to make sure that no cycles are created is union find onto the runtime. So we make E number of operations into the priority queue, and each of those operations takes log E time. And since this is the operation in the algorithm that dominates, the runtime is E log E. Any questions? Okay. Yeah, okay, so as an example, we're going to implement Kruskal's algorithm on this graph. And this is a question from the spring 2017 final. They also asked to write out the edges in the order that Kruskal's includes them in the minimum spanning tree. Yeah, I'll give a minute to work on. Okay, does anybody have an idea of how they would do it? Okay, if not, we'll just start. Yeah, so we, oh, yeah, so we can start. So the first thing that you do in Kruskal's is we find the minimum weight edge, and over here that's going to be EF because it has a weight of 2. Since it doesn't create a cycle, we're going to add that to the MST. So that's the first edge that we add. After that, we're going to find the minimum weight edge again, and that's going to be 3. BC with a weight of 3, and that doesn't create a cycle, so we add it to the MST. We repeat that process, and now, yeah, something to keep in note is that the question asked us to break ties by alphabetical order. So even though BE and BG both have a weight of 4, we're going to include BE first. On to the next one. Now, yeah, so BG also has a weight of 4, so that's the next edge that we add into the MST. And after this, the minimum weight after 4 is 5, which is CE, but we're not going to include this because if we do that, it's going to create a cycle between B, C, and E, and so we discard that. And so the next one with the minimum weight is the edge AB, which has a weight of 6. That doesn't create a cycle, so we add that. And now if you can see, we only have D left to include in the tree, and which is going to be the edge CD with a weight of 9. Doesn't create a cycle, so we add that, and that's the minimum spanning tree. It looks like this for better clarity. Yeah, any questions about how we did this? Okay. Yeah, so on to Prim's algorithm. So Prim's algorithm utilizes the cut property that we went over a few minutes ago. So the main idea is that we start at a start vertex, and then you use the cut property to find the next smallest edge to include in the minimum spanning tree. And you continue to do this until all of the vertices have been included in the minimum spanning tree. And the implementation is the same as Dijkstra's, but the only difference is that we have the priority queue stores and updates vertices by their distance to the minimum spanning tree that's being constructed instead of like a source node. And so the runtime is the same as Dijkstra's, and if we assume that the number of edges is more than vertices, we have E log V runtime. Okay, so the implementation of Prim's algorithm, what we're doing when we make the cut is we basically divide the graph into 2 sets. One set is the vertices that have already been incorporated into the minimum spanning tree, and the other set is those that haven't been included. Okay, so this is a question from fall 2020, and they've asked us to make a minimum spanning tree using prims on this graph, so I'll give a minute to work on it. The starting node is P. Does anyone have any ideas on how to approach this? Okay, if not, we'll just get started. Okay, so we start at the start node, which is P. And then what we're going to do is we're going to draw a cut, and the cut is going to separate the graph into vertices which have already been included in the minimum spanning tree and those that aren't. I've colored them for reference. So this is going to be the first cut. And as you can see, the edges the crossing edges over here are AP and DP with weights of 8 and 9. And we want to pick the one with the least weight, and that's going to be PD with a weight of 8. And so that's going to be what we include in the minimum spanning tree. And then the next thing that we do is we draw another cut. This time it's going to be traversing these 3 edges. The edge DN has the minimum weight of 3, and so that gets included. So we have DN as the next edge, and we've now included vertices PD and N. The next cut is going to be across these 3 edges, and the minimum weight is AD with 4, and that gets included. And remember that we're also making sure that there's no cycles that have been formed. After this, as you can see, so the yellow vertices have been included in the minimum spanning tree and the gray ones haven't. And so the next cut is going to be across those, separating those types of vertices. And now the one with the minimum weight is AI with weight 1, so that gets included. Onto the next one, we have this cut, and then IR has the least weight of 2, and so that gets included. And then VA with a weight of 6. And then the last one is the edge VJ with a weight of 7. And so that concludes Prim's algorithm, and you have every single vertex that's been included. Yeah, for clarity. Any questions about how this is done? Okay. Yeah, so now for some conceptual questions. So yeah, so they're asking us to describe an algorithm to find a maximum spanning tree rather than minimum, and the algorithm has to use Kruskals without any modifications. So I'll give a minute to work on this. Okay, yeah, there's a question in the chat about how we draw the cuts. So so you draw the cuts in such a way that, so you have your vertices, you have 2 groups of vertices. One is the ones that have been included, the ones that aren't, and the edges that connect those 2, that connect vertices from both of those sets, those lie under your cut. So these 3 edges, they each have like a vertex in the yellow set and the gray set. Okay, I hope that answers it.
In that case,
Mm-hmm.
in like that one, if not in that, yeah, in that one, if JV will have been like 1 and AI will have been 7.
Oh yeah, okay, sorry. That should be a smaller line. Thank you. Okay. Yeah. So for this question, what you can do is, yeah. Anybody has any ideas for this one? Okay, so since Kruskals basically finds a minimum spanning tree by ordering the edges from in increasing order, and we've been asked like not to modify Kruskals, what you can do is negate every single edge weight and then run Kruskals, and that's basically going to get you a maximum spanning tree. Yeah. Okay. Next question. Adding 1 to the smallest edge across any cut of a graph must change the total weight of the minimum spanning tree. Any ideas? Yeah, okay. So so the smallest edge, you know by default that it's going to be included in the minimum spanning tree. And so if you're modifying that, the minimum spanning tree is also going to be modified in terms of its weight. And in the other case where if it's not included, we're going to
be including a larger edge, and so that is still going to change the overall weight of the minimum spanning tree. So that's going to be true. And then for the next question, which is given any cut, the maximum weight crossing edge is in the maximum spanning tree. So a maximum spanning tree is basically a spanning tree with edges that maximizes the total cost. So it's essentially the same as minimum spanning tree, but we're just favoring edge weights with higher values. And so what we can do is we can run Prim's algorithm and we can take the largest edges across the cut instead of the smallest ones. So the cut property will still apply. We just replace larger with smaller. So that's also true. Any questions? Okay. Yeah, I think that's it.
So thank you so much for coming again. If you have the time, we'd really appreciate it if you could fill out our feedback form. Every semester we try to improve on these review sessions. This semester was a bit of a challenge due to the strike. So we appreciate all of you coming today. So again, if you have the time, please go ahead and fill out this feedback form. And good luck on your final. Happy studying. All right, thank you. And if you have any questions, I'll be sticking around. I think some of the other mentors will also be sticking around, so feel free to ask your questions. Okay.